Hello students, welcome back to my channel, and today I'm going to discuss about class 10. The chapter is again real numbers. So before I go to the name of today's topic, I just want to discuss something with you. You take any prime numbers collection, like I'm taking only two, that is 2 and 3. Suppose you can take 2, 3 and 5, and somebody can take 2, 3, 5 and 7, whatever it is. I'm multiplying this. 2 into 3 will be 6, 2 into 3 into 5 will be 30, 2 into 3 into 5 into 7 will be 210, and so on, right? Now the main thing is that we can see that when we are adding, means when we are multiplying new prime factors, we are getting new numbers as their product. Okay, now you can introduce one particular prime factor's power also, like this. Suppose 2 square into 3 into 5 will be 60. Okay, 2 square into 3 into 5 equals to 60. Now look, this one and this one, they both are having 2, 3 and 5 as prime factors, but 60 has two 2's and 30 has 1 2. 60 has two 2's and 30 has 1 2. Okay, so these two are ultimately different. In this way, if we go on, then obviously we can do like this: 2 to the power 3, 3 to the power 7, whatever, 5 to the power 4, and dot dot dot, and we will be getting some number here. Okay, now when we are writing all these things and getting different products for different kind of expressions for prime factors, different powers of prime factors, then just tell me, can you get any composite number which doesn't, means which, whose factorization when we will do, we will not get any prime numbers? I'm repeating my question again. Can you get or can you find a composite number during whose factorization you will not get any prime factor? Can it be possible? No. Because you, after multiplying all these prime factors, we are getting composite numbers only. Okay. Now you must be thinking about 1. Now 1 is non-prime, non-composite. Okay, 1 is a unique number. So 1 is not prime, not composite. So we will not look into 1. Except 1, all natural numbers you take, all positive integers you take, either prime numbers or composite numbers. And composites, when we are doing its factorization, we will be getting some prime factors. Okay, so from that we can conclude roughly one thing, that any composite number, a composite number can be expressed as product of some prime factors. Okay, product of prime factors. Okay, so any composite number will be product of prime factors, and those prime factors expression will be unique. What does it mean by unique? Let me give you some example, then it should be more clear. For unique, I am taking 2 into 3, I am getting 6. Okay, I am taking 2 into 2 into 3, it will be 12. Now look, when maybe I am having prime factors as 2 and 3 in both the cases, but you can see their expressions. Here 1 2 and here 2 2's. So ultimately their prime factorizations expressions are also different, and that means we can say that 6 has only this prime factorization. Can you imagine 6 with any other factorization except 2 and 3? No. Can you imagine 12 with any other factorization except 2 into 2 into 3? No. That means for any composite number, it can be expressed as a product of prime factors, and that expression of prime factorization will be unique. And this whole mathematical statement is fundamental theorem of arithmetic. Fundamental theorem of arithmetic. And this is today's first topic. Fundamental theorem of arithmetic. It tells that, means its exact statement is that any positive integer or any composite number can be expressed as product of prime factors, and that expression will be unique. Expression will be unique. Now, depending on this fundamental theorem of arithmetic, we have some of the examples and exercise 1.2 also. Now, fundamental theorem of arithmetic tells that we will have unique factorization. So there is a very important type of question that is really very important for board exam. That is question I am writing. Okay, and then I will be explaining it. Check whether 6 to the power n can end with the digit 0, where n is natural number. This is the question. We need to verify, we need to check whether 6 to the power n can be any natural number. Suppose 6 to the power 1, 6 to the power 2, 6 to the power 3, like this. So these expressions will never end with the digit 0. We have to check it. So I have already answered it. It will never end with the digit 0. How? Look into the process. 6 to the power n is the given number here. I'm taking for n equals to 1. Okay. For n equals to 1, we get 6 to the power 1. 6 to the power 1 means 2 into 3. And we can write 2 to the power 1 into 3 to the power 1. Right? Then for n equals to 2, 6 to the power 2. That means 2 to the power 2 into 3 to the power 2. Dot 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 6 to the power n will be 2 to the power n into 3 to the power n. Now you can see this expressions. 6 to the power n can be anything. Only 2's powers, 3's powers will be changed. There will not be any number except 2 and 3. Because fundamental theorem of arithmetic says 6 can have only 2 and 3 as its factors. Okay? Now, so we have got 6 to the power n into 2 equals to 2 to the power n into 3 to the power n. So what's the problem of ending with the digit 0? What's the problem? Here we need to know one basic thing. First, you choose any number coming to your brain ending with the digit 0. If you ask me, I would like to choose 10 first, because that's the first one ending with the digit 0. So 10, for 10, what's its prime factorization? 2 into 5. For 20, it will be 2 into 5 into 2. For 30, 2 into 5 into 3. 40, 2 into 5 into 2 into 2. Suppose dot 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 100. 2 into 5. Suppose 400. 2 into 5 into 2 into 5 into 2 into 2. 400. Now, can you see any similarity in all these expressions? Yes. What's the similarity? This 2 into 5 factor. This 2 into 5 factor means 1, 2 and 1, 5 is always there in the factorization. This leads us to the conclusion. Means for any number to end with the digit 0, means for any number, if you want to have the digit 0 at the end, means here in units place, we must have at least 1, 2 and 1, 5. At least 1, 2 and 1, 5. Everywhere you can see it can be more than 1. Here 3 2's are there, no problem. Here 2 5's and 4 2's are there, no problem. But minimum 1, 2 and 1, 5 are there. So this is the criteria, this is the condition to have the end digit 0. But now look at this. If you go on to infinity also, then also you will not get 5 anywhere. 2 is there, but 5 is nowhere. And for a number to end with 0, we need 2 and 5 together. We need 2, 5 together as a bunch. Here 2 is present, but 5 can't come as 6 is not a multiple of 5. Okay, so we will write that Simply I am writing the statement also as for number to end with 0, it must have at least 1, 2 and 1, 5 as its factors. Here 6 to the power n will never have 5 as its factor. Therefore 6 to the power n can never end with the digit 0. Okay, and this is the way of writing. First you do this, then you write the statement from here, because this is the logic. So this logical statement must be there to get its full marks. Now this can be anything, like this can be 8 to the power n, then 8 to the power n will be 2 cube, 8 square will be 2 to the power 6, 8 to the power n will be 2 to the power 3n, n will be 2 to the power 3n, and in this way 2 to the power 3n means only 2 is the factor, there is no 5 and there is no chance to get 5 for 8's prime factorization. That means 8 to the power n can never end with 0 with the same logic, same reason. Okay. So this is the first ever application of fundamental theorem of arithmetic. We will move on to the next application. Next application, actually the name maybe you are learning now, but its application already done in previous classes. Okay. So the second application is to find out HCF and LCM by prime factorization. Now look, prime factorization itself gives the idea of fundamental theorem of arithmetic. That means this is also an application of fundamental theorem of arithmetic. Now let me take two numbers. Here in your book it is given 510 and 92. 510 and 92. So we will do its prime factorization first. 510 prime factorization, 2 2s are 2 5s are 2 5s are 5 5s are 5 1s are 3 17s are. Now we have come to a point where all are prime factors, so we will stop here. For 92, 2 4s are 8, 1 2 2 6 are 2 2s are 2 3s are 23 is a prime number, so we have to stop here. Now look, 510 equals to 2 into 3 into 5 into 17. 5 5s are 5 1s are 5 2s are 2 5s are 5 3s are 5 1s are 5 2s are 2 3s are 5 4s are 5 5s are 5 6 are 5 7s are 5 8s are 5 9s are 5 10s are 5 11s are 5 12s are 5 13s are 5 14s are 5 15s are 5 16s are 5 17s are 5 18s are 5 19s are 5 20s are 5 21s are 5 22s are 5 23s are 5 24s are 5 25s are 5 26s are 5 27s are 5 28s are 5 29s are 5 30s are 5 31s are 5 32s are 5 33s are 5 34s are 5 35s are 5 36s are 5 37s are 5 38s are 5 39s are 5 40s are 5 41s are 5 42s are 5 43s are 5 44s are 5 45s are 5 46s are 5 47s are 5 48s are 5 49s are 5 50s are 5 51s are 5 52s are 5 53s are 5 54s are 5 55s are 5 56s and 92 equals to 2 into 2 into 23. Okay, now HCF will be the common factor. What is the common? Is there any other common factors? No. So highest common factor is 2. There is nothing else common. So 2, 1, 2. That means its HCF is 2. LCM is, you have to take one time common factor, that is 2. LCM is equals to 2, one time common factor, and then rest all whatever left. So 2, 23 into 3 into 5 into 17. And you have to multiply it. Not now, because this will be very, very lengthy and will obviously take the time. So whatever will be its answer, that will be LCM. Now this is obviously direct application of prime factorization, and that means fundamental theorem of arithmetic. Okay, now there is a formula depending on HCF and LCM. The formula or the property is, suppose A and B are two numbers, then HCF of A comma B into LCM of A comma B is equals to A into B, okay? HCF A comma B into LCM of A comma B is equals to A into B. Its statement can be written in what statement form like this: product of two numbers is equals to product of their HCF and LCM. So this is one property. Now from this property, if you know A, if you know HCF, LCM, you can find out B. My point is that there are 4 terms. If you know any three of them, then the fourth one is very easy to find out. So students, applying this formula and the previous one that just I discussed, applying these formula, these theorem of arithmetic, prime factorization, you can do the sums given in the exercise 1.2, except question number 6. Question number 6 is little bit different, so we will be doing this one in the next session. So this was all about today's session, students. I hope you all have understood it. So we will meet in the next video with any other topic. Till then, have a good day.